Okay, hello. So uh, today we are going to finish the sensor board. This is part two of the sensor board design, and we are to add the GPS based on this image right here. You are to add the GPS and get started on the PC-104 bus connection. So the module I choose for GPS, the Neo 6M modules were not available. They have been given the end of life by blocks. So this is Neo 6M GPS. You can see that they have this is an older generation product, so we cannot use this series of modules. So I found this other one called ATG-M336 GPS module. This one right here, let's see. This is the data sheet. So it has precision of around 2.5 meters, which I can work with, and it can receive all these satellite systems. The one I'm most interested in is a GPS satellite system, American obviously. So there are also these Chinese, whatever, BDS, Russian and whatnot, but the GPS is okay. So it's in manufacture, it's in in the market. I can use that. Plus, if we look at cold start, time to fast fix is 32 seconds, which is okay. 25 milliamps at 3.3 volts, which is fine. This is a block diagram you can see there. Then if we look at obviously we have the SMD components, 1.5 to 3.6 volts. VBAT VCC is 3.3 volts. Okay. Then if we look at the block diagram, this circuit, so you can see there's an antenna at this point. There's a filtering bead here, 47 nanohenries. VBAT 3 volts, 10 microfarads to filter the 3.3 volt capacitor. So then there is the EWAT, RX and TX, and then this 1 PPS signal. So let us do that. So what I'll do, obviously the first thing I do is I search here ATGM 336. I can place this one. So copy that and bring it here and place it. So I'll place it right there. So the first thing, ground. So ground here and ground on top here. Ground. Okay, then I label these two, RX and TX. So this will be GPS. GPS or TX. So they'll go to the onboard computer RX, and this will be GPS RX, because the TX of the onboard computer. The next lines I see here next are the reserved ones. So this is reserved. This is reserved. I put not connect. I'm not using I2C, so I put those ones, and also the not connect right there, not connect. Okay. Then there's of course another ground here, so I can do that, connect right there. And then I did RF, but before that, let me work on these other signals. So I want like full control of this GPS module from the onboard the flight mission software. So I'll root this on, off, reset, PPS, all these ones I'll root them out, so that when I send the AT commands, I can be able to control this device. I can turn it off and turn it on whenever I need to. Ideally, because when you're not using the GPS for a satellite, you want to save power, so you can turn it off and turn it on back again when you need really to get a GPS fix. For example, when you are doing the data dumping, when it's like crossing over your base station, or when it is in range. All right, so that's that. I need to label these ones. PPS on, off, reset. So this will be one PPS. This is GPS on, off. This is GPS reset. Okay, VCC receives 3.3 volts, so I can give 3.3 volt here. Let's see. Let me move this one a little bit. Let me move it a little bit here just to create some space. And then VCC it's right there. And then I need what capacitor do I need? Where is the okay? Capacitor I need is 10 microfarads. So I'll use a 10 microfarad capacitor here. 10 microfarad capacitor. So this is 0.05, 10 microfarad capacitor. Okay. Ten microfarad capacitor. Where is it? It should be showing here. Yeah. 10. Okay. Copy the number. Bring it here. Paste. And place it. So this should come right here. I can do that. And that is in order. The remaining thing is the RF. So let me just break these out a little and say here is this is RF. Okay. So they need or they're recommending a 47 nanohenry between RF and VCC RF. VCC RF is right here. So I'll put a pin label here and say this is VCC RF. Okay, VCC RF. Let me push this a little bit and then move the spaces. I mean, I can make the page size big, but I won't be able to print this thing on a normal A4 size paper. So I look for 47 nanohenry. So the current should be, I think, less than, from what they said, should be less than 25 milliamps. We should be able to handle 25, should be more than 25 milliamps, so that we can be able to handle this current. So I'll open this guy and search for 47 nanohenry. a ferrite bead. 47. It is supposed to be 47. Let me look for inductor. Okay, this is 47 nanohenries, 200 milliamps, which is good. It has a series resistance of 100 milliamps. This is 950, 720. I think this is okay. And it is SMD, so I can use that correctly. So paste place. Just place between what? Between VCC and RF in. So I'll copy this, put it right there, and copy this guy and put it right here. Then just connect those two. Okay. So that's that. Then from RF to the antenna symbol. So from here to the antenna. And from here. So for the antenna, I need an SMA. I mean, no, not an SMA. I need a. I keep forgetting the name for that connector. U.FL mail. Yeah, this one. U.FL mail cable. This is the cable. This is what I'm talking about. All right. So let's search for that. E.FL and see whether it's available. Nope. Let's search for antenna, see what they give us. Yeah, this is what I'm looking for. And it's in stock. So I can take that, paste. It's not available there. How about this other one? Paste. That's also not available. This other guy should be available. All right, cool. So I can place this one right here. So these two are ground, then the middle pin is the input pin. So I'll put that right there, RF, and I ground these two guys. I ground these ones. Ground. Ground that. Okay. So RF is done, and I think we are good. What I can do here, I can connect this guy just to make it more visually, understandable. I can do that like that. Okay. I think we are done with the GPS. We are done with the GPS at this point. When we review the schematic, we will be able to maybe see what we did not notice. Oh yeah, we left the VBAT. I think GPS. Left VBAT. So VBAT will come from the EPS board. So this will be VBAT of VBAT. Let me say GPS. GPS BAT. All right. So that's that. That should be okay. Right. Now, save that. Now, the next thing we want to look at is this bus here. This is the PC-104 bus. So what I'll do, I'll explain how I intend to use it in this project, and then we can figure it out later, like in terms of the physical connection. So a PC-104 bus ideally is a protocol or standard that is used to connect embedded computers that are size constrained. So if you have a very small space and you want something that can be very, very rugged and compact, this is the most common bus that is used. So it allows you to stack uh, boards on top of each other. And if I open, let me open GitHub and show you what I'm talking about. There is a project. Okay. I think did I push that? I did. Good. Okay, so this is the README from the project. PC-104 bus, yeah, good. So this is a PC-104 bus. It is stackable, first of all. It's interoperable, means that you can remove boards and use in other designs without having to worry about which pin is connected to what pin. It's very easy to add functionality. What is required is just to route that functionality to an empty pin or a pin that is not used. Then it's compact and rugged, can handle a lot of shocks and vibrations. So it's highly recommended in the industry. Like for example, industrial setups, satellites, CubeSats, space systems, military and stuff. So this is called the ISA connector that employs or that PC 104 employs. So 104 is from the number of pins. This guy has a standard 104 pins. So you can see at the bottom here, they are extended such that you can stack two boards or more than as many boards as you need, just limited by the power supply you have and the space requirements or constraints and maybe the physical dimensions of your project. But you can stack as many as you want. So these boards are separated by standoffs. You can see these standoffs here, also defined in the standard documentation. Excuse me. So there's a reference document that I have open here. So this document was written by this consortium here, and they said that this is a PC-104 specification, 2008. Okay, there's a lot of information, the pins, the addresses. So they tell you like what they expect the standoff height to be. This is 15.24 millimeters spacers, and this other side they are like that. And when you put them together, this should be 15.24 millimeters. So the height from board to board can be 15.24 plus the thickness of the board, which is approximately 1.6, assuming 1.6 millimeters. Yeah. And then there is a signal definition. So this one is standard, but you can tweak it based on your mission requirements or your project requirements. So I've put a link to this document and you can download and look at it if you want. Then there is a mechanical dimensions. So this explains, this is a form factor we'll be using for our PCBs ideally. First of all, because the length of this board from this point to this point is less than 100. Actually is 90. This is 90.17 centimeters, which fits within our new dimensions or constraints. And then the height is also less than 100. Yeah. Then they give you the locations of these standoff mounting holes, and then the connector is given at that point. All right, and then there's a cross-section view at that point. You can see. So now this is the ISA connector I was talking about. It has 104 pins. That's what we're gonna use. Cool. It's a standard. It's very rugged. So for a satellite, it's gonna work perfectly. All right. So what I've done, I have come up with a diagram here that tries to break out or to assign the pins to a different. It's a bus, so I want to assign different pins or a bus lines to the PC-104 bus. Yeah, so I have an image from the document specification right here. So what I've done, I've put all the grounds where they're supposed to be. If you look closely, you can see this ground is matched to this ground. All these grounds are matched right here. You have where is 5 volts? 5 volts is right here. Positive 5 is here. Ground, okay. Ground on the top. So basically that's what I've done for the power lines. And then now, because I don't have most of these, I won't have most of these buses, for example, the interrupts and whatnot, I can explicitly define my own assignments. So for example, I've put pin 2 here to be an SDA pin and SCL, just like you can see labeled GPS, RX, TX, etc. Now, this thing can help you carry 16-bit data or 8-bit data. So for the specification document, they say that if you're using 8-bit, you don't need this second part. This is 40 pins. You don't need these 40 pins here. These are 64 pins. You can use this one only. If you're using 16-bit data bus, you need to use both of them. So I don't think I'll have as many lines as this, but I'll use as many as I can based on the number of sensors and data lines that I have on my CubeSat. And then I leave the rest such that later on I can extend the device, or rather I can extend the avionics of the CubeSat without having to change a lot of design specs. So that's that. I've added this link also to the README. So if you want to look at it, you can look at it and try to understand how it works if you want. But yeah, so this is basically the PC-104 bus. So right now I'm not going to add it here on the schematic because I've not designed all the other boards. So I'm not done designing the EPS, the onboard computer. So I won't add it yet until I have defined all the lines that I need. Okay. There's a GitHub one. Yep, this one. So you can see really it makes your board look very, very, very neat. If I show you a picture of a PC-104 stacked design image, this is how it looks like. This is how it's supposed to look like. Something like this. You see? Ignore these other PCI Express and 104 Express and etc. Just this PC-104. So basically you can see the connector, the standoffs, etc. And this is the model you are going to adapt for our CubeSat. All right, so I think that's enough for today, and I'll see you next time for the next video. Bye bye.